All right, hi everybody. Today we're going to start a new lecture on quantum mechanics. And the material here comes from chapters 6 and 7 of volume 3 of our textbook. Chapter 6 gives you some of the historical developments that led up to quantum mechanics. And chapter 7 is full on quantum mechanics. So we're going to do both of those. So to introduce this idea, let's contrast where we're going, which is to study quantum mechanics, quantum physics, with classical physics, which is basically the physics you know up until this point. So in classical physics, the state of a system is given by the position and the velocity of all its parts. So you have different objects, they have different positions, they have different velocities, but if you know all the positions and all the velocities, you basically know everything there is to know about that system at any given moment in time. Then what you can do is predict how that system is going to behave at a future time using something called a dynamical law. Okay, so we know the state of the system at one moment, we predict the future state of the system using a dynamical law. So the dynamical law you're probably most familiar with at this point is Newton's second law. That's F equals ma. So let's just kind of sketch out an example of this, something you've done a million times before, as far back as physics 44. So let's say we have a box sliding down a ramp, okay? And so what we do is we look at the forces acting on the box. You have a normal force, you have a frictional force, and then you have gravity. And of course, we can break everything into X and Y components, as you see here. But the idea of this is we can plug those forces into the equation, F equals ma. And what happens? You can calculate the acceleration of the box down the ramp. So if you know the acceleration of the box, and you know the starting position and the starting velocity, you can then predict what the final position and the final velocity will be sometime later, okay? So that's just an example of what I sketched out here, right? We have the initial state of the system, that's the starting position and velocity of the box. We use the dynamical law, that's F equals ma, to predict the final position and the final velocity of the box anytime later. Okay, so that's the approach we know, and it works extremely well for everyday situations. But if we want to describe physics at the very smallest scales, I'm talking about the level of atoms and molecules, it turns out this approach breaks down. Classical physics just doesn't work at the smallest scales. And so what we need is a new, more powerful theory, and that's called quantum mechanics. So quantum mechanics was developed in the early 1900s to explain a lot of features of the atomic world that couldn't be explained by classical physics. And I'm going to show you some of those things in a second, where classical physics fails to describe certain things that happen at the atomic scale. But just remember, in classical physics, we specify the state of a system by giving definite values for position and velocity. So every single moving object in our system, we keep track of its position and we keep track of its velocity. And position and velocity have definite values. We can just assign some number to position and velocity. But the thing is, in quantum mechanics, we actually can't know the exact position and velocity at the same time. And this is what's known as the Heisenberg uncertainty principle. We're going to get into this later on in the lecture. But the point is, we're going to have a very different approach for quantum mechanics compared to classical mechanics, because we can't just specify the state of our system by giving a position and a velocity. So in quantum mechanics, the state of our system is given by something called a wave function, okay? And a wave function is given by this variable psi, okay? That's the Greek letter psi. And the dynamical law in quantum mechanics is no longer F equals ma. It's actually something called the Schrödinger equation. And basically, if you solve the Schrödinger equation, you can calculate the wave function for your quantum system. So there's a whole lot more to go into as far as how that works and what the wave function actually means, but this is just a preview as to where things are going, okay? And again, quantum mechanics is going to be very different from classical mechanics in a lot of ways. Okay, so that's just a brief roadmap as to where we're going. Now let's get into the historical development of quantum mechanics. So what discoveries were made that led up to the development of quantum mechanics? And we're going to start with blackbody radiation. So first, let me explain what blackbody radiation is. Basically, in a nutshell, blackbody radiation is the light that is emitted by an object because of its temperature, okay? All matter with a temperature greater than absolute zero is going to emit light. And the reason for this is, okay, what does an object really consist of? It consists of a bunch of atoms and molecules. And as we learned earlier in the semester, those atoms and molecules are undergoing random motions. They basically vibrate, jiggle around within the object. Okay, well, atoms and molecules consist of electric charges, right? Positive and negative charges. And when you have an electric charge that's wiggling around, vibrating, it gives off light. Okay, so any object with a non-zero temperature is going to give off light. Basically, what's happening is the thermal energy in those jiggling atoms is converted into electromagnetic energy. That's just a fancy way of saying it's giving off light. Okay? So there's this word black body. What does that mean? Any object that absorbs all EM radiation, that's electromagnetic radiation, that hits it and reflects no electromagnetic energy back is called a black body. So it absorbs everything and it doesn't reflect anything when light hits it. So any black body has a characteristic spectrum of the light that it emits. And this spectrum depends on its temperature, okay? So what I'm showing you down here are some graphs of different black body spectra for different objects. What you see on the vertical axis is the intensity of the light that gets emitted. And what you see on the horizontal axis is the wavelength of the light that's being emitted, okay? So what do we notice? Let's look at this curve first. This is showing you the black body spectrum for an object with a temperature of 5,000 degrees. So what does it do? At very short wavelengths, it's emitting very little light, so the intensity is low. The intensity shoots way up, and then it peaks somewhere, and then it goes back down. And the same is true of this curve over here, which is for a cooler object at 4,000 K, and the same is true here at 3,000 K and 200 K. So every temperature has a given black body curve, okay? And we notice that the higher the temperature, the higher the overall intensity, right? So the 5,000 Kelvin curve has the highest peak intensity. But also we notice that at higher temperatures, the wavelength where the peak intensity happens is shorter, okay? So for example, this object at 5,000 Kelvin, the peak of its black body spectrum is in the visible range, right? But if we go down to 2,000 Kelvin, the peak of its spectrum is actually now in the infrared, so it's not even visible, right? And actually, this explains something you've probably seen before, which is if you take a piece of metal and you heat it up to a very high temperature, it will appear to glow, right? You can actually see the black body radiation that it emits. That's because, again, at higher temperatures, the peak of the intensity happens at shorter wavelengths, and it can be even pushed as far as the visible range, right? But if this same piece of metal were much cooler, you wouldn't see its light being emitted, right? That's because its black body spectrum peaks outside of the visible range, so you don't really notice the light that's being given off. So now I want to tell you about two very important experimental results that were discovered by people working on this problem of black body radiation back in the late 1800s, okay? So the first one is called Wien's displacement law. This says that the higher the temperature of the object, the shorter the wavelength where the peak intensity occurs. And this is what I showed you on the graph. So the way we say this is lambda max, which is the wavelength where the peak intensity occurs, times T, that's our absolute temperature in Kelvin, equals some constant, which we're going to call B. Okay, and this constant has a value. This is experimentally measured to be 2.898 10 to the minus 3 meters times Kelvin. Okay. Then we have what's called the Stefan-Boltzmann law. This gives the total power radiated by a black body. So remember, power is energy per unit time being radiated by the black body. So according to the Stefan-Boltzmann law, this depends on both the surface area of the object and the temperature of the object. So here it is. P is equal to this constant called sigma. This is called the Stefan-Boltzmann constant, times A, that's our surface area, times T to the fourth power. So this depends on the fourth power of temperature. So you can see that the power is going to grow very rapidly as the temperature grows. Anyway, this constant sigma is 5.670 10 to the minus 8 watts per square meter per Kelvin to the fourth power. The units are a little weird, but it just makes it so that the P value works out in units of watts, which is our power unit. So let's do an example where we use both of these experimental results. So here we have the sun. The sun has a radius of 6.96 10 to the 5 kilometers, and it has a surface temperature of 5,780 Kelvin. Question is, what is the total power radiated by the sun in units of watts? And then at what wavelength does the sun radiate the most strongly? So we're going to give that wavelength in nanometers. All right, so let's work this out. Let's start with the Stefan-Boltzmann law, which states that the total power radiated P is equal to this constant sigma times A times T to the fourth power. Now, we're dealing with the sun, which has a spherical shape, so the area should be the surface area of a sphere, which is 4 pi times the radius of the sphere squared. So we'll make that substitution for the surface area. And now we're in a position where we can just plug and chug. So, okay, we have the Stefan-Boltzmann constant, which is 5.670 times 10 to the minus 8 watts per square meter per Kelvin to the fourth power. Okay, and then we have 4 times pi. Then we plug in the radius. The radius of the sun was 6.96 times 10 to the 5 kilometers. However, we want this to be in units of meters. So if we just multiply by 10 to the 3, now we're in units of meters. And then we have to square that. And notice how meters squared is going to cancel. Okay, and then we have the temperature. Again, this has to be given in Kelvin for this to work, but that's what we have. So we have 5,780 Kelvin, and we have to take that to the fourth power. So notice how units of Kelvin to the fourth power also cancel, and we're just left with watts. And if you do the calculation, you'll get 3.85 times 10 to the 26 power watts. And that is actually extremely close to the actual experimental value. Okay? So we also want to calculate the peak wavelength. So that's lambda max. So the Wien's displacement law says lambda max times the temperature T is equal to this constant, which we're calling B. Of course, if I want lambda max, that's just going to be equal to B over T. Okay, so that's pretty simple. The constant B is 2.898 times 10 to the power minus 3. And the units here are meters times Kelvin. And then we divide out the temperature, which is 5,780 Kelvin. And notice how Kelvin cancels, and we're just left with meters. Okay. This comes out to 5.014 times 10 to the minus 7. And that's in units of meters. We want this in nanometers. So what's the unit conversion? In every 1 meter, we have how many nanometers? 10 to the 9 nanometers. Okay. So if you multiply that all out, you're going to get 501 nanometers. And notice this is right in the middle of the visible range. That's not a coincidence. Basically, our eyes evolved to detect light that's being emitted by the sun. We want to be very sensitive to that kind of light because it illuminates our surroundings. So it makes sense that this is the peak wavelength where the sun is emitting. It's right in the middle of the visible range. Now, everything I've told you about up until this point are just experimental results dealing with blackbody radiation. So scientists went into their labs, they studied the spectra of different blackbodies, and they found that they obey the Stefan-Boltzmann law and they obey the Wien's displacement law. But ideally, you'd want to go a little bit farther than that. You want to have some kind of theoretical model of blackbody radiation. In other words, you want to take what you know about physics and apply it to the problem of blackbody radiation and just see if you can calculate the correct blackbody spectrum, right? The one that we experimentally know is true. All right, so people at the time tried to do this, and it led to a huge disaster. So when we take classical electromagnetic theory, this is Maxwell's equations. If you take Physics 46, you'll learn about Maxwell's equations. If you try to apply that to the problem of blackbody radiation, what you get is a very bad prediction. The prediction that you come up with is that the emitted intensity blows up to infinity at small wavelengths. So we obviously know what actually happens, right? I showed you in the graph 2 slides ago that at small wavelengths, the intensity actually goes to 0, right? But the prediction of classical electromagnetic theory is that it blows up to infinity. So not only is that wrong in the sense that, the prediction from our theory doesn't match the actual data, but it's kind of nonsensical. Like, how could you have infinite intensity? So this is an obvious failure of classical physics, and this came to be known as the ultraviolet catastrophe because ultraviolet wavelengths, we're predicting that the intensity goes to infinity, which is obviously wrong. So there needs to be some kind of correction here. And this is a hint that we need to go beyond classical physics. We need some kind of new physics. So in the year 1900, there was a German physicist by the name of Max Planck who came along and solved this problem. So in Planck's model of blackbody radiation, he assumed that blackbody radiation does come from atomic vibrations within an object, so vibrating atoms give off light, but he assumed that those atomic vibrations can only have discrete values of energy. So they can't just take on any given energy value, they can only take on very specific discrete values of energy. And when he made that assumption and did the calculation, he came up with the exactly correct blackbody spectrum. So Planck's model works, classical models do not work, okay? So let's talk a little bit more about how his model works. If we look at this equation at the bottom of the slide, we have E, that's the energy of our vibrations, is equal to N times H times F. So F is the frequency of the vibrations. We're familiar with that. H is a constant, which we're going to get to in a second. It's called Planck's constant. It's one of the fundamental constants of nature. And N is an integer. So it can only take on discrete values, 1, 2, 3, and so on. It can't take on a continuous range of values, right? For example, 1.5 doesn't work, 2.5 doesn't work, right? Only these discrete values, 1, 2, and 3, and so on, actually work. So the energy can't take on any given value. It can only take on certain discrete values, okay? Now, that may seem a little strange. Why can the energy only take on certain values and not others? We're going to get to that in a bit, but for now, let's just say it works, okay? This works. Classical physics does not work to describe a black body, okay? So, in Planck's model of black body radiation, as I said, the atomic vibrations that lead to this light being given off can only have discrete energy values. And this idea is known as the quantization of energy. And this is going to come up a lot in quantum mechanics. In fact, notice quantization, quantum kind of share a similar root. So what do we mean by the quantization of energy? Again, this is what Planck's formula says. The energy of the vibrations is n times h times f, where n only takes on these integer values. So the energy is quantized. It can only take on very specific values. Okay. So in this formula, we have this constant called h, which is known as Planck's constant. And this basically sets the size of the gap between the possible energy levels. So, I mean, let's take a look. Like if n is equal to 1, right, then we just have h times f, right? And if n is equal to 2, then we have 2 times h times f. And then if n is equal to 3, then we have 3 times h times f, and so on. So the gap between energy levels is just h times f, right? So h is setting the size of the gap between the energy levels. All right. This constant was experimentally measured to have the value 6.626 times 10 to the minus 34. And the units here are joules times seconds, okay? Now, in the equations of quantum mechanics, you're often going to see a different value for this constant, which is called h bar. Okay, h bar is known as the reduced value of Planck's constant. And it's really simple. H bar is just h over 2 pi. So if we take this value of h and we divide out 2 pi, we get h bar. And you can calculate this if you want. It comes out to 1.054 10 to the minus 34 joules times seconds. So the equations of quantum mechanics sometimes have h, just Planck's constant, and other times they have h bar, the reduced value. So just know the difference between the two, okay? All right, so we talked about blackbody radiation. That was maybe one of our first hints that there is some new physics going on beyond classical physics. Another important effect is the photoelectric effect, which also hints at some new physics beyond classical physics. So the photoelectric effect, we did briefly talk about this before, is when light hits a metal surface and then ejects electrons off the metal. So the picture you should have in your mind is this. We have a metal surface down here, and it contains a bunch of free electrons. These can be used to conduct electricity. But for now, they're just sitting there, right? Now, we have some incoming light hitting the surface. That light gets absorbed by the electrons in the metal, and if they have enough energy, they can be kicked off the metal and just fly outwards, okay? So that's the photoelectric effect. Incoming light kicks out electrons, okay? Now, this is an effect that was studied experimentally a lot in the late 1800s. And there are two important experimental results that I want to highlight from all these different experiments that were going on at the time. So the first one is that the kinetic energy of the ejected electrons, we're going to call that K, depends on the frequency of the light that's hitting it. So that's F. But it does not depend on the intensity. So that seems a little weird when you look at it, because you might expect if you have very low intensity light, right, it's going to maybe not even kick the electrons out at all, or if they do get kicked out, it's going to be at a very low kinetic energy. And then if you have higher intensity light, then we kick the electrons out at a higher kinetic energy. That's probably what you'd expect, but it doesn't work that way. The intensity is totally irrelevant. The only thing that matters is the frequency of the light. And then also we notice that electrons are not ejected at all if the frequency of the light is below a certain cutoff frequency, which we're going to call Fc. So all of these results are nicely encapsulated in the graph that you see at the bottom of the slide. So on the vertical axis, we have K, which is the kinetic energy of the outgoing electrons. And on the horizontal axis, we have F, which is the frequency of the light that's hitting the metal surface. Okay, so the general shape you're going to get on this graph is a straight line like this. where you notice that if the frequency goes up at higher frequencies, the kinetic energy of the outgoing electrons is greater, right? And as the frequency gets lowered, the kinetic energy of the outgoing electrons also gets lower. But this can only go on for so long, because at a certain point, the kinetic energy of the outgoing electrons is 0, okay? And that's where the frequency is equal to Fc, okay? Because the lowest possible kinetic energy for the outgoing electrons is 0, can't go negative. So this is the lowest frequency where we can actually kick out electrons. So any frequency above this is going to end up with electrons being ejected. And then any frequency below this is not going to result in electrons being ejected. So nothing will be emitted from the surface at frequencies below the cutoff. Now, different metals are going to have different lines on this graph. So for example, if this is metal number 1 shown in red, this is metal number 2 shown in blue, and you can see they have different cutoff frequencies. That's generally going to be the case. And we can also imagine extrapolating these lines back. Okay, so this is not actual data. This is just an extrapolation of the line backwards, shown with the dashed line, until we hit basically the vertical axis. Okay, now the energy value that we hit as we extrapolate back is called phi. Okay, and I'm going to explain what this is in a second, but just take note of the fact that we have phi 1 over here for the intercept for metal number 1, and we have phi 2 over here as the intercept for metal number 2, okay? So let's talk about now Einstein's model of the photoelectric effect. So again, the photoelectric effect is an example of something that classical physics is really not equipped to explain, okay? So we need some kind of new physics, and Einstein came along in 1905 and gave this model of the photoelectric effect that actually works. So what Albert Einstein proposed in his model is that the energy of the incident light is quantized. Okay, so we're dealing with quantization of energy once again. And in his proposal, each electron absorbs exactly one particle of light, which we call a photon. And the energy of that photon is given by E equals h times F. So the idea is one photon comes in, it's absorbed by exactly one electron, and the energy of that photon is given by h times F, okay? And the idea is, if the photon has enough energy, it might be able to kick the electron out, and if that photon doesn't have enough energy, then it won't kick the electron out. And if the energy just depends on the frequency, that explains why certain frequencies are enough to kick electrons out, and if the frequency is too low, it's not enough to kick an electron out. And this number h is coming into play once again. That's Planck's constant from before. F is, again, the frequency of the incident light. Okay, so now let's explain what that phi thing from before was. Phi is called the work function of the metal. And basically, that's just the energy that's required to remove an electron from the surface. Okay, so it's going to take some energy to actually remove the electron from the surface because it's bound to it, it's attracted to it in some way. So however much energy it takes just to remove the electron from the surface, that's called phi, the work function. So what we can do is apply conservation of energy to the interaction of this one photon and this one electron, and we can come up with this equation you see at the bottom of the slide. So what's the idea behind this equation? There is a photon, it comes in, and it gets absorbed by an electron. So when that happens, the photon is gone. It no longer exists. It's just given up all its energy to the electron, okay? So what was the energy of that photon? We can think of this like the initial energy, right? What was just h times F, according to Einstein's model, right? And then what's the final energy? This is the energy that's given to the electron. Well, it basically consists of two parts, right? You have phi, that's how much energy it takes to actually kick the electron off the surface, and then plus k. Any additional energy the electron has after it's been removed is just going to be kinetic energy in the electron flying off at some speed, okay? So again, the initial energy of the photon that gets absorbed is equal to the work function, that's how much energy it takes to remove the electron, plus kinetic energy that it has after it's been removed, okay? Now, in a second, I'm going to show you an example problem where we go over the photoelectric effect and do some calculations with that equation we just came up with. But first, I want to take kind of a detour and talk about units, okay? So specifically, we're talking about a new unit of energy that you might not have seen before called the electron volt. So the electron volt, given by EV, is a unit of energy that's commonly used in physics when we're talking about subatomic particles. So remember, a joule is the SI unit of energy, and it's pretty useful when you're talking about macroscopic objects, but it's probably not the most convenient unit to use when you're talking about like an electron or something like that. So what is an electron volt? 1 eV is the amount of energy that's gained by an electron when it moves through a potential difference of 1 volt, okay? So if you had like a 1 volt battery, let's say, an electron moved across the terminals of that 1 volt battery, it would gain 1 electron volt of energy. That's how it works. Now, we know how to convert the units. 1 electron volt is the same thing as 1.602 times 10 to the minus 19 joules. So this is a unit conversion that you're going to do quite a bit when you're dealing with quantum mechanics. So just keep that one in mind. And also keep in mind that we can use our unit prefixes that we've used before. So I'm talking about things like kilo and mega and milli and things like that. So for example, KeV is kilo electron volts, MeV is mega electron volts, and GeV is giga electron volts. So we can always attach the unit prefix. Let's do a few examples where we use this unit. So first example is, how much kinetic energy does an electron have if it's moving at 2.1 10 to the 6 meters per second? So we're going to calculate this in units of EV. The mass of an electron is given here. It's 9.11 10 to the minus 31 kilograms. Okay, second example is, how much kinetic energy does a mosquito have if it's moving at 1.5 meters per second? And we're going to calculate this in units of EV once again. The mass of a mosquito, kind of varies, but let's use this value, 2.5 milligrams. All right, that's going to be our M value. So let's do these calculations. Let's do the first example, which was for the electron. Remember, kinetic energy is given by 1/2 m times v squared, okay? So we have 1/2. What's the mass of the electron? That's 9.11, 10 to the minus 31 kilograms. And we have v, which is the speed, and we have to square it. So it's 2.10, 10 to the 6th power meters per second, and we square that. And this comes out to 2.009, 10 to the minus 18 joules. We're actually going to keep 3 sig figs on that. And also notice that unit-wise, what we have is kilograms, meters squared per second squared. That's the same as a joule. So just remember that from before. Okay, so now we want to take this and convert it over to electron volts. So the conversion factor is 1 electron volt is equivalent to 1.602 10 to the minus 19 joules. Okay, so joules cancel. We just have electron volts at the end of this. And if you do the computation, should come out to about 12.5. Okay, so that very fast moving electron has an energy of 12.5 electron volts. Okay, so that was example number 1. Let's do example number 2. This is the mosquito. All right, same kinetic energy formula applies. So let's plug in everything we know. It's 1/2, and then M is the mass of the mosquito. Okay, so this was 2.5 milligrams. Okay, so remember, milli is 10 to the minus 3. So now we have 2.5 times 10 to the minus 3 grams. But we want to get this in kilograms, so we need another factor of 10 to the minus 3 to get it in kilograms. Okay? So there we have it. That's the mass now in kilograms. And then we multiply by 1.5 meters per second. That's the speed, and we square that. All right, so if you calculate this, it comes out to 2.81, 10 to the minus 6 joules. And if we go ahead and convert that to electron volts using the same conversion factor as before, so I'll just write that down again. What ends up happening? We get 1.76, 10 to the 13 electron volts. We actually want to keep 2 sig figs on this one. I can rewrite this after rounding as 18 times 10 to the 12. 18 times 10 to the 12 electron volts. And notice 10 to the 12 is the unit prefix tera. So this would be 18 tera electron volts, TeV. Okay, so here's an example where we're actually going to make some calculations dealing with the photoelectric effect. So the work function for potassium is 2.26 eV. Remember, that's the amount of energy it takes to remove an electron from the surface of potassium. When light of frequency 1200 terahertz hits a potassium surface, what is the energy of the ejected electrons in electron volts? And then calculate the speed of those outgoing electrons in meters per second. Okay? And then the next thing we want to do is we want to calculate the lowest frequency of incident light for which electrons will be ejected. In other words, what is the cutoff frequency? Okay, so to do these calculations, we need to know a few things. This is Planck's constant, this is the mass of an electron, and then this is the conversion factor between electron volts and joules. So that's basically everything we need to know. So pause the video, try to work this one out, then come back to it once you have some answers. All right, let's work this one out. Now, let's start by applying conservation of energy to the interaction of one photon and one electron in the photoelectric effect. So remember, the idea here is the energy of the incident photon is equal to the energy that gets imparted to the electron. The reason for this is that the electron absorbs the photon. The photon is just gone afterwards. So in order to conserve energy, the electron needs to take on all the energy that the incident photon had. So remember, the energy of the incident photon is hf, according to Einstein. And the energy imparted to the electron has these two parts. Okay, we have the work function phi, which is how much energy it's going to take to kick the electron out, and then plus k, which is any remaining energy it has after that, which is kinetic energy. Now in this first question, we're trying to solve for the kinetic energy, so let's do that. K is equal to, looks like we have h times f minus phi, right? Okay, so we can do this. H is Planck's constant, so that's 6.626, 10 to the minus 34. The units are joules times seconds. Okay, F is our frequency. So that's 1200 terahertz. 1200 times 10 to the positive 12 inverse seconds. That's 1200 terahertz for the frequency. All right, and then we have minus phi, minus the work function. The work function we're given is 2.26 electron volts, but let's be careful. We need the units to be consistent. We want the units to be in joules here to start off. So to convert this from electron volts to joules, what we do is we multiply by 1.602. So we have 1.602, 10 to the minus 19 joules. Okay, so that's the work function in joules. Okay. So what do we get as a result of this? We get 4.331 sig figs times 10 to the minus 19 joules. Okay. And if we go ahead and convert that over to electron volts, basically that means we have to divide by this number now, right? What we get is 2.7 electron volts, okay? So if we hit the potassium surface with this frequency of light, we're going to be kicking out electrons such that they have this much kinetic energy, 2.7 electron volts, okay? All right, now we remember that kinetic energy is equivalent to 1/2 mv squared. So if we know the kinetic energy, we should be able to calculate the speed v pretty easily. So v squared, if we solve for it, is 2 times k over m. And if we square root that, we get v. So root 2k over m. All right, so v is equal to, now let's be careful. We want to kind of decide which unit we want to use. We better use units of joules here in order for the result to come out in meters per second. I'll show you why that is in a second. So if we have 2 times k, that's 2 times 4.331, 10 to the minus 19. This is in joules, so that's the same as kilograms, meters squared per second squared. That's what a joule is. And we're going to divide by the mass, which is, for an electron, 9.11, 10 to the minus 31 kilograms. And then we're going to square root that. So notice kilograms drops out. And then we just have meters squared per second squared under the radical, so that's meters per second. So how many meters per second is this? It's 9.8, 10 to the 5. So that's how fast the outgoing electrons are moving. Okay. The last question here is, what is the cutoff frequency? All right, well, let's think about this. If we want to find the cutoff frequency, remember that's the lowest frequency of the incident light for which we will still kick out electrons. And anything below the cutoff frequency, we're not going to kick off electrons, right? So remember, the kinetic energy of the electrons is always a positive quantity, or it can be 0, right? So what we could say is k is greater than or equal to 0. And this is just another way of saying the kinetic energy can't go negative. Forgot how to spell. Can't be negative. Okay. So the minimum value the kinetic energy can have is 0, right? So if we basically set the kinetic energy in our equation to 0, here's what happens. We have h times fc, that's our cutoff frequency, equals kinetic energy minimum plus phi. And again, we're setting the kinetic energy minimum to 0, so we have h times fc is equal to 0 plus phi, which just means fc, our cutoff frequency, is equal to phi over h. So it's just the work function divided by Planck's constant. All right, so these are numbers we know. The cutoff frequency is the work function, which is 2.26 eV, electron volts. So that's, sorry, I meant to say 2.26 eV, 2.26 times 1.602, 10 to the minus 19. Now we're in joules, right? And if we divide by h, which is Planck's constant, that's 6.626 times 10 to the minus 34 joules times seconds. Okay. So notice the units we end up with are inverse seconds. So we have 5.4 0.464 10 to the 14th power inverse seconds. That's the result you get when you calculate this. But remember, inverse seconds is the same as hertz, and 10 to the 12 is the unit prefix tera. So I could also write this as 546 terahertz. That's the cutoff frequency. Anything above this is enough to eject electrons, but anything below this is not enough to eject electrons. So up until this point, we've talked about the photoelectric effect and blackbody radiation. These are two examples of physical phenomena that can't be explained by classical physics and where we need to come up with some new physics to accurately describe what's going on. So atomic spectra is just another example of that sort of thing. So what's going on here? If we take a sample of atoms, let's say just hydrogen atoms sitting in a tube, and we pump some energy into that sample. For example, we could do this by applying a voltage to it or just by heating it up, whatever the case may be. That sample of atoms is going to give off light, okay? And it turns out we can do this to different chemical elements. Like we could do this for hydrogen, we could do this for helium. And what we'll find is each chemical element has its own characteristic spectrum. And we can study this spectrum by basically passing the light that gets emitted through a prism, so we can break it up into its individual wavelengths, okay? Now, what we find is, regardless of what type of element we use, that atomic emission spectra are always discrete. So that means there are certain bright lines in the spectrum where light is being given off. Let's say this red line in the hydrogen spectrum and then like this blue line in the hydrogen spectrum are where light is being emitted, but there are gaps in between, okay? So it's completely dark in between those lines, and that means no light is being emitted at these wavelengths over here. So that's what we mean by discrete, okay? The atom gives off light at very particular wavelengths, and it does not give off light at wavelengths in between. Now, this is the atomic spectrum for hydrogen. It only has 4 lines in the visible range, and it has other lines outside of the visible range. So it's a pretty simple spectrum. If we look at, as another example, the atomic spectrum of iron, it still has these discrete lines, but notice there's a whole lot more of them, and it's a much more complicated spectrum. That tends to be the case as you basically go up in atomic number in the periodic table, tend to get a much more complicated looking spectrum, but the basic idea still remains, okay? Atomic emission spectra are discrete, meaning we only emit light at very particular wavelengths, and we don't emit light at wavelengths in between, okay? So atomic emission spectra are just another example of something that classical physics really can't explain. In classical physics, you would never expect that the light that gets emitted is only at discrete wavelengths with, gaps in between. So what comes along is the Bohr model of the hydrogen atom, and this is able to explain the emission spectrum of hydrogen. So in 1913, the physicist Niels Bohr came along and proposed that electrons in the hydrogen atom are orbiting the nucleus, but they have energies that are quantized. So once again, this idea of quantization of energy is coming into play. So in the Bohr model of the hydrogen atom, this is what you should be picturing. We have a nucleus, which just consists of a single proton that has a positive charge, and it just sits at the center of the atom, doesn't move. Then we have an electron, which has a negative charge, which is orbiting the nucleus. So you can kind of picture an electron orbiting the nucleus, just like the Earth orbits the sun. Now, this is not a very accurate picture of what's really going on in the atom, okay? We can't really think of the electron as moving in a circle around the nucleus. It's more complicated than that. But for the Bohr model, this is good enough to get us where we need to go. Okay, so we have this electron, it's orbiting the nucleus, and it has a certain energy as it orbits. But in the Bohr model, the energies are quantized. So it can't just take on any energy. It can only take on certain discrete values of energy. So let's call this energy E1. This is the energy the electron has when it's orbiting at this distance over here. And this is the minimum energy that the electron can have. If we have energy E2, it's orbiting at a greater distance out here. And then if it's at energy E3, it's orbiting at an even greater distance. And you can see how as the energy goes up, the electron gets further and further out from the nucleus. Okay, but again, there's gaps in between, so it can't just take on any energy level. The way we can describe this mathematically is like this. E sub n is equal to minus E1 divided by n squared, where E1 takes on this value, 13.6 electron volts, and n takes on integer values, so 1, 2, 3, and so on. So let's just take a look at what happens, let's say, when we plug in n equals 1. If n equals 1, then I just have minus E1, so I have minus 13.6 eV. That's the minimum energy that the electron can have. Is minus 13.6 eV, right? If I plug in n equals 2, I get that same value, but now divided by 4. So I get a bigger amount of energy, less negative number, right? And you can plug in any integer value and you can get the available energy levels, okay? Now, how does this relate to the light that gets emitted by the hydrogen atom? Well, when the electron transitions between energy levels, let's say like the electron goes from the n equals 1 level, jumps up to the n equals 2 level, or maybe it can jump down in energy level. Maybe it starts at n equals 3 and jumps down to n equals 1. Whatever the case may be, it has to either absorb a photon or emit a photon in order to account for that energy difference, okay? So the idea would be if we jump up in energy level, the electron is gaining energy, so it has to absorb a photon to gain that energy. And if it jumps down in energy level, it's going to emit a photon, so it can give off that energy and have less energy than before. So the energy of that photon is equal to h times f, but that's equal to basically the difference in energy between the final and the initial energy state. So it's E final minus E initial. And we use the absolute values here because this could potentially be negative, right? We could be losing energy if we jump down in energy level, but we just want to use the absolute value here to give us the energy of that photon, okay? So the Bohr model is able to accurately reproduce the emission spectrum of hydrogen. You can use this model to predict at what wavelengths do you expect hydrogen atoms to emit light, and it's completely accurate. It agrees with the data, but it actually fails for larger atoms. And the reason for that is the Bohr model doesn't account for the interactions between electrons. So you need a slightly more sophisticated model. But this takes us pretty far in explaining certain aspects of atomic physics. So let's do an example here. We have a hydrogen atom that transitions from the n equals 1 state to the n equals 3 state by absorbing a photon. So just a little terminology here. We often call the n equals 1 state the ground state because it's the lowest energy level that the electron can have. And we call states that are higher than that in energy excited states. So n equals 3 would be the second excited state. So that's the second state above the ground state. Okay, so the question is, what is the energy in units of electron volts of this photon that has to get absorbed? And also, what is the frequency and the wavelength of this photon? So a couple useful numbers here. We have Plancks Constant and the conversion between joules and electron volts. So before we get into the solution, let me just show you an animation as to what's going on here. So we have this photon coming in. It gets absorbed by the electron. The photon is gone now, and the electron gets kicked up from the n equals 1 state to the n equals 3 state. So pause the video, try to work this one out on your own, and then we'll go through it together. All right, so here we're basically applying conservation of energy to the situation. And that looks like this. Let me just state it in words first. The energy of the absorbed photon has to equal a change in energy of the electron. So this is the change in energy of the electron. And again, the reason for this is the electron absorbs the photon, so the photon is gone after that, and any energy the photon initially had has to be given to the electron. So that's basically what we're saying here. Now, for the energy of the absorbed photon, I'm going to write this as E gamma. That's because gamma is a symbol that's often used for photons in physics. So we'll just say E gamma for the energy of the photon. And like I said, this is E final minus E initial for the electron. That's the change in the energy. So for E final, I can write that as minus E1 over N final squared, just using the Bohr model. And then for E initial, which I'm subtracting, I have minus E1 over N initial squared. So I can pull out an overall factor of E1 if I need to. And I can write this as E1 times 1 over N initial squared. So there's two negative signs next to that term, so it's overall positive. And then minus 1 over N final squared. Okay, so we can just plug in numbers. E1 is 13.6 eV. And N initial is 1, because I start off in the ground state. So I have 1 over 1 squared. And then N final is 3, because I end up in the second excited state. So this is 1 over 3 squared. Okay, so that's just 1 minus 1 over 3 squared. That's the same as 1 minus 1/9. So this overall is 8/9 in the parentheses there. So what you're doing is 13.6 eV minus, multiplied by 8/9. Okay, do that calculation. It's pretty straightforward. It gives you 12.09 eV, which we're going to round to 12.1 eV. So that's the energy of our photon, is 12.1 eV. We can find the associated frequency of that photon using this formula. The energy of the photon is equal to h times f. We've seen that before. So if I want to solve for f, that's the energy of our photon divided by h, Planck's constant. Okay, let's do the calculation. The energy of our photon is 12.09 eV, but if I multiply that by 1.602, 10 to the minus 19, now we're in units of joules. And if I divide that by h, Planck's constant, that's 6.626, 10 to the minus 34 joules times seconds, I can see that my resulting unit is inverse seconds, and that's the same as hertz. That's what I would expect for a frequency, right? So anyway, it comes out to 2.923, 10 to the 15th power, inverse seconds, which I could also write as 2,920 terahertz. Remember, tera is 10 to the 12, so that's how we could write the frequency. Now, how can I find the wavelength of the photon? Well, for the wavelength of the photon, okay, I can just use the fundamental relationship between speed, wavelength, and frequency, which is c, the speed of the photon, that's the speed of light, equals lambda times f. So lambda should just be c divided by f. And remember, c is 3 times 10 to the 8 meters per second. And F is what we just found. It's 2.923 10 to the 15th power inverse seconds. Now what this works out to is 1.026 10 to the minus 7 meters. This will come out in meters. But we can convert that over to nanometers, and it's 103. So this is outside of the visible range. This is ultraviolet. This is UV light. And yeah, that's the energy, frequency, and wavelength of the photon. So the picture that starts emerging in the early 1900s is that light, which traditionally was considered just to be a wave, has some particle-like properties. So in order to explain things like the photoelectric effect and the emission spectra of atoms, we need to think of light as consisting of photons, which are particles. Okay, so in 1926, the French physicist Louis de Broglie comes along with a proposal, which initially sounds kind of crazy, but let's just hear him out. He proposed that all matter, which is traditionally considered to be made of particles, we're talking about atoms, molecules, things like that. He proposed that all matter has wave-like properties. So according to de Broglie, any particle that has energy E and momentum P has an associated wave with a frequency of F and a wavelength of lambda. So that's a lot to say. Let's put it into equations. So in other words, if our particle has energy E, it also has a certain frequency associated with it, which is given by, well, this formula. E is equal to H times F. So in other words, this doesn't just apply to photons. This applies to particles of matter, like atoms and molecules and so on. And in addition to that, there's a wavelength, okay, which is given by this formula. P is H over lambda. P is the momentum, lambda is the associated wavelength, and H is Planck's constant. So energy is associated with frequency somehow, and momentum is associated with wavelength. Okay, that's de Broglie's hypothesis. Now, as strange as it may seem to say that a particle has a wave-like property to it, this was actually confirmed the very following year in 1927 in something called the Davison-Germer experiment. So roughly, this is what was done in the experiment. Electrons were shot out at metal surfaces, and the scattering of those electrons off the surface was observed. Okay? And in this experiment, it was demonstrated that electrons exhibit diffraction when they scatter off these metal surfaces. So remember, diffraction is something we think of as a wave phenomenon. Diffraction happens because waves that are emitted off the surface are interfering with each other in different ways and creating this diffraction pattern that we've seen before. You wouldn't expect electrons to do that if you think of an electron as a particle, okay? So the fact that electrons do exhibit diffraction shows that they do have this sort of wave-like property to them. And not only that, if you calculate the wavelength of those electrons that you get given your diffraction pattern, it exactly matches the formula that de Broglie came up with. So it's, in other words, the wavelength is equal to H over P, where P is the momentum of those electrons. So this is a confirmation of de Broglie's hypothesis. All right, so with that said, and again, this may be a little weird, it maybe hasn't quite sunken in yet, let's just do an example where we calculate the result of this equation. So calculate the de Broglie wavelength of a 652 gram basketball, which is thrown at a speed of 10 meters per second. In other words, lambda is equal to H over P. Let's do that calculation of lambda for this basketball. Just see what we get. And then let's do another one. Let's calculate the de Broglie wavelength of an electron with a kinetic energy of 1 eV. Okay, in order to do these calculations, we'll need to know a few things. Planck's constant is given right here. the mass of an electron, and the conversion between electron volts and joules. So again, pause the video, see if you can just calculate these numbers, and then we'll talk about what it means in a second. Okay, so we'll start by doing the calculation for the basketball. And again, the formula for the de Broglie wavelength is lambda is h over p, where p is the momentum. So we have to remember that the definition of momentum is P equals mv. It's just mass times velocity. So for the wavelength, therefore, we have h divided by mass times velocity. Okay? So we can plug the numbers in. It's pretty straightforward to do that. For h, we have Planck's constant, that's 6.626 times 10 to the minus 34. And the units here are joules times seconds. But I just want to show you a useful relationship. Joules times seconds is the same as kilograms meters squared per second squared, that's a joule, times a second. So overall, we have kilograms times meters squared per second. Okay, so one of the factors of seconds just cancels, and that's what we get. So I'll write that on top. We have kilograms meters squared per second. That's the unit for h. Okay, and then we have the mass, which is 652 grams. If we put that in kilograms, that's 0.652 kilograms. And then v is the speed. That's going to be 10 meters per second. Now, notice how the units almost completely cancel, but the only thing we're left with is a unit of meters on the top. So that's what we expect. We're talking about a wavelength here. And if you do the calculation, you'll get 1.016 times 10 to the minus 34 meters. We can round that to about 1.02 times 10 to the minus 34 meters. Now, it's worth taking a look at that number and just appreciating how small it is. Okay? So what's something really small we could compare this number to? So 10 to the minus 10 meters is the atomic scale. This is the size of typical atoms, 10 to the minus 10 meters. That's way larger than the number we just calculated. In other words, the wavelength we just calculated is so small that it makes atoms look just gigantic, okay? So in other words, we get unimaginably small wavelengths for everyday macroscopic objects like a basketball, which is why we don't really notice the wave-like properties of macroscopic objects like a basketball. But if we do the same calculation for the electron, here's what we get. So first of all, we can't do the exact same calculation because we're given an energy, not a speed for the electron, so we have to do a little work. Let's write down the formula for kinetic energy. That's 1/2 mv squared. Now, it looks very similar to the formula for momentum in a lot of ways. It just involves mass and velocity. So we could do a little bit of manipulation here. We could say this is 1/2m times m times v squared. I could write it that way. And m times v is just the momentum. So that would just be p, the momentum squared, divided by 2m. So that's just another way of writing the kinetic energy. So if I solve this for the momentum, I have p squared equals 2m times k. And that means the momentum is the square root of 2m times k. Okay? All right, so if that's my momentum, I can plug that into my formula for the de Broglie wavelength. Lambda is h over p, so that's going to be h over the square root of 2 times m times k. Okay, so we have h, that's 6.626, 10 to the minus 34. and the units are kilograms, meters squared per second. And then we're dividing out the square root of 2 times m times k. All right, we're talking about an electron here. So the mass is 9.11, 10 to the minus 31 kilograms. K is the kinetic energy, and that's 1 electron volt. Okay, that's 1 eV. But we better put that in joules to make the units work out. So 1 electron volt is 1 times 1.602, 10 to the minus 19 joules. And a joule is the same as a kilogram, meters squared per second squared. Okay, so all I did there was just go from electron volts to joules, and then I wrote the unit joules in kind of an expanded way. So I'm not going to fully go through this, but if you analyze the units here, you can see that it works out just to meters, as we expect. And what you get is 1.226 times 10 to the minus 9 meters. Okay, and that rounds to about 1.23. And then remember, 10 to the minus 9 is nano, so we could say 1.23 nanometers. Okay, that is a pretty significantly larger wavelength than for the basketball. And for a basketball, something macroscopic sized, this wavelength is just negligibly small. But for an electron, a couple nanometers might be an appreciable distance. So the takeaway of this is the wave-like properties of matter, okay, that de Broglie is proposing are really only significant at the smallest scales, or they're only noticeable at the smallest scales. And that brings us to this idea of wave-particle duality. The question you should have in your mind after going through this lecture is, how should we think about the universe at its fundamental level? Like, what are electrons and photons and things like that? Should we think of them as little spheres with definite locations that fly around space and bump into each other? Or should we think of them as like waves that are spread out over space? So if you've been following along, you'll know that sometimes we've been using this sort of particle model, and other times we've been using this wave model. So what's the deal with that? How can we have both of these pictures in our heads at the same time? Well, Albert Einstein had a nice quote about this, so I'll just read it to you. It seems as though we must use sometimes the one theory and sometimes the other, while at times we may use either one. We are faced with a new kind of difficulty. We have two contradictory pictures of reality. Separately, neither of them fully explains the phenomena, but together they do. So what he's saying here is there are some physical effects that are best explained by thinking of things as particles, right? Like thinking of photons and electrons as being particles. There are other physical effects that are best described by wave models. And it looks like separately, neither one of those models fully encapsulates what's going on, but together somehow they do. So the true nature of the fundamental particles is still debated. But it seems like these concepts of waves and particles that humans use don't fully capture what's going on. There's something else beyond these simple concepts of waves and particles that we need to start to understand. And that's where this idea of a wave function is going to come in. So in the next lecture, we're going to talk about wave functions, which is not going to fully solve this mystery that we've set up here, right? But it'll get you a little bit further into understanding it. So that's it for today.